MIT researchers have introduced a quantum computing architecture that can perform low error quantum computations while also rapidly sharing quantum information between processors. The work represents a key advance toward a complete quantum computing platform. Previous to this discovery, small-scale quantum processors have successfully performed tasks at a rate exponentially faster than that of classical computers. However, it has been difficult to controllably communicate quantum information between distant parts of a processor. In classical computers, wired interconnects are used to route information back and forth throughout a processor during the course of a computation. In a quantum computer, however, the information itself is quantum mechanical and fragile, requiring fundamentally new strategies to simultaneously process and communicate quantum information on a chip. One of the main challenges in scaling quantum computers is to enable quantum bits to interact with each other when they are not co-located. While natural atoms are small and point-like with respect to the wavelength of light they interact with, in a paper published in the journal Nature, the researchers showed that this need not be the case for superconducting artificial atoms. Instead, they have constructed giant atoms from superconducting quantum bits or qubits connected in a tunable configuration to a microwave transmission line or waveguide. This allows the researchers to adjust the strength of the qubit waveguide interactions so the fragile qubits can be protected from decoherence or a kind of natural decay that would otherwise be hastened by the waveguide while they perform high fidelity operations. Once those computations are carried out, the strength of the qubit waveguide couplings is readjusted and the qubits are able to release quantum data into the waveguide in the form of photons or light particles. The system realized by the researchers represents a new regime of light-matter interactions. Unlike models that treat atoms as point-like objects smaller than the wavelength of the light they interact with, the superconducting qubits or artificial atoms are essentially large electrical circuits. When coupled with the waveguide, they create a structure as large as the waveguide of the microwave light with which they interact. The giant atom emits its information as microwave photons at multiple locations along the waveguide, such that the photons interfere with each other. This process can be tuned to complete destructive interference, meaning the information in the qubit is protected. Furthermore, even when no photons are actually released from the giant atom, multiple qubits along the waveguide are still able to interact with each other to perform operations. Throughout, the qubits remain strongly coupled to the waveguide, but because of this type of quantum interference, they can remain unaffected by it and be protected from decoherence, while single and two qubit operations are performed with high fidelity. The coherence time of the qubits interconnected into the giant atoms, meaning the time they remained in a quantum state, was approximately 30 microseconds, nearly the same for qubits not coupled to a waveguide, which have a range between 10 and 100 microseconds. Additionally, the research demonstrates two qubit entangling operations with 94% fidelity. This represents the first time researchers have quoted a 2 qubit fidelity for qubits that were strongly coupled to a waveguide, because the fidelity of such operations using conventional small atoms is often low in such an architecture. With more calibration, operation tune-up procedures and optimized hardware design, the fidelity can be further improved.